dark energy. And as some of this serves as a background because a lot of the problem with dark energy, right, has to do with language, has to do with people not defining their terms or using concepts as physical objects. And that's where we draw the line. We have to stop them there and say, look, concepts are over here, objects are over there. Every word in the dictionary falls under one of those two categories. Objects we can point to and name and say that's it. And it's an object, it's got shape. And concepts, first, don't have shape, and you must define them.
I was telling him yesterday that what he does in a lot of ways is very much like coding or programming, because you have to define your variables rigorously. You have to have a very
the computer needs to understand it.
You need very clear definitions, whether it's a number you're talking about or a word you're talking about, or what category it's in. It's very, very rigorous. Like you can't cheat, or else the computer will not understand you.
Yeah,
but the thing is, with humans, you can get away with murder because we're very poetic. since we can kind of I see what you're saying.
Yeah, that's one of the issues that we do a lot of poetry, especially people who want to do physics.
Yeah.
That's one of the problems. The other issue is that
the running boy fell sounds like a normal thing to us.
A lot of people got used to using the language that they were taught in high school, especially, right?
Well,
and they never questioned, how we're using concepts as physical objects. I mean, you look at any textbook of physics, and where does it start? It starts by telling you about concepts. This is force, okay? And this is mass, and this is acceleration.
Yeah.
All those are concepts. Physics is about object. You can't do physics without an object. So the first thing you have to define is the word object, and not a single textbook of physics on planet Earth ever defined the word object. But the thing is,
I just think it's very interesting how you got very programmery with your physics.
And I was going to say about
that's
that.
when you get into real nitty gritty.
Okay, and I wanted to say about that. In a computer, if you don't program, what you were saying now, if you don't program the word in the right way, the program doesn't know what to do.
Yeah.
There you have to be very specific, very objective.
It's worse. Yeah. You won't know what you meant. That's what I was trying to tell you.
Well, I care about the ChatGPT.
No,
he doesn't know that we're in trouble.
But it comes back to the just understanding physics in general.
Yeah.
If I'm reading my own codes sometimes and I've named a variable in a way that I don't understand, I won't know what I meant 2 months ago, which adds to all the confusion. Where I'm like, okay, what did I mean? Like, forget if I believe whatever. Just understanding what is on paper is hard because the variables are all misnamed.
So let's get on with dark energy. And for this, we have to understand how this thing started, more or less, okay? It starts with the Big Bang. That's relativity's version of how our universe began. I said a minute ago that the universe never began. It's always been there. Mathematics has reached a different conclusion. They said, look, there was an explosion 14 billion years ago. Some call it an explosion. Other people don't like the word explosion, but that's why... they say it's not really an explosion, and it's a long story.
It goes, woof. What else is that?
They say it's not a hand grenade, that just exploded. But it is. It ain't, but it is. Okay, and here it is. This is the way they visualize it.
A bunch of stuff flying out of an epicenter.
We had this. Okay, there was this explosion.
Yeah, that's not an explosion. It's just a very.
That's a hand grenade that exploded, throwing all this debris.
That's quick expansion. That's
and the first dot that you see, just as soon as it appears, that's known as the singularity. How that singularity got there, they say, well, that's an unscientific question because we have no way of verifying or testing or whatever. Okay, so what the religious people will do is say, hey, we agree with you, but you forgot to put God in the picture.
Yeah,
God created
God
the singularity.
was one frame before that.
Right.
Very easy.
But see, the so-called scientists, the mathematicians, they don't like it. Okay, so what happened? We
just missed them. God just came by.
So we had this explosion, okay? And this is what happens. This is the sideways view of this. It explodes, and it builds this little cup, this little glass, tilted glass, right? And what you're seeing there, each one of those lines, that's time. Okay, so you can see that the explosion led to this time thingy. And that last one, the W map there, that's covering the end of the cup, that's our present state. In other words, that's a cross section of time, and we're all living on that flat universe, as they call it, because they believe in the flat universe.
So not flat Earth, but flat
no,
universe.
they're not flat.
We've
Earth.
upgraded.
Are you crazy? No, it's a flat universe.
We've upgraded.
So we live on that flat universe, okay? But then what they do is they show it in this way, okay? Because you have to visualize it in this direction for us to understand it in our 3D world. And it's like this, okay? You're supposed to see it like that. Our universe is a ball that is exploding. It's a balloon that's inflating, okay? And as you can see, all the galaxies there are flying apart. And the little curlicues, that's light. The light is being stretched as the universe expands. And of course, people have one question usually, and they say, well, what's the white stuff that gives shape to the ball? And that's when they say, well, it's an unreasonable question. It's an unscientific question because on the one hand, the universe is not expanding into anything. That's one answer that you get. And the other one is, well, we don't know, and we have no way of proving it.
Well, wait, hold on. We got the gray stuff that's expanding, but what's also the white stuff of the backdrop? We have two questions.
But that's the question. Well, the gray stuff is space. That's why the white stuff is not space.
Okay, so white stuff is the gray stuff is space.
Yeah, we know that what space is. That's a gray stuff that's expanding. Really, it's not space. Sorry, I will qualify that. It's space time.
That's even worse.
Okay, it's a space time. This is a 3D version of our 4D universe. Okay, so it's you're supposed to imagine it in 4D if you can, and we don't know what the white stuff is. Maybe it's the 5th dimension, 10th dimension.
What are the yellow dots?
And the yellow dots, you can think of those as stars or galaxies, and the curlicues are light going from one galaxy to the next. Okay. As the universe expands, it stretches light, the wavelength of light. Okay.
Does that mean that light?
And that's why all the galaxies are red shifted, meaning they're receding from us because light takes longer and longer to get our.
But worse. Keep that gift there. Does this mean that light doesn't
travel at the same speed or what?
Something like that, because the distance is getting.
Yeah, but remember,
you know what I mean?
No, but remember the issue. The issue here is that
if I'm running away from you and I turn a light on, there's more distance for the light to travel.
Not for light, because Einstein said light always travels at the same speed.
Yeah, okay.
No, but hold it. You got to understand it. That's where the equation comes in. Little c, 300,000 kilometers per second, is equal to wavelength times frequency. Meaning, when the frequency goes up, wavelength goes down, and vice versa. That means all you're doing is stretching the wavelength, but that means now you have a lower frequency.
But the light is still taking longer to get.
Not
because it's traveling slower, but the distance is getting bigger.
Yeah, but that's why they're saying that all these galaxies, we'll never get to them because they're flying away faster than light, or even faster than light. Yeah. Because the universe is ballooning faster than light can travel. That's the.
Wouldn't that mean that they're just standing in place? If the balloon gets bigger faster than light, then we shouldn't be able to even see any other galaxies.
Yeah, but
the light never gets to us.
Yeah, of the distant ones, the ones that are closer by, they're not as faster than light. But the ones distant that are farther away from us,
some regions are getting further away faster than other regions?
The farther a galaxy is from us, the faster it's receding from us.
Okay.
So the ones closer, we can see those, but the day will come when we can't see those either.
Jesus.
Okay, so who came up with all this stuff? Well, here we have our three heroes: George Lemaitre, Albert Einstein, and Edwin Hubble. Edwin Hubble was an astronomer. He looked there. He said, "Hey, all the galaxies are receding. They're all redshifted." And George Lemaitre essentially said that he came up with this Big Bang notion. Albert Einstein never believed in the Big Bang theory. Okay, some people dispute that, so they're still. I guess the jury is still out. But good old Albert, he did not approve of a lot of stuff that they made of his theory. He never believed in quantum mechanics. He didn't believe in black holes. In fact, he did talk about that. He wrote papers against that. He didn't believe in gravitational waves. And there's a fight of whether he believed in Big Bang or not. I take the position that I haven't found proof, evidence, in his writings that he actually believed in Big Bang theory.
Do you think all the physicists were just kind of waiting until he died so that they can put a bunch of words in his mouth? You know what else he said? He thought my theory was true too.
They made a hero of him.
Yeah, but it's like they're waiting. Come on, I need you to die so that we can fill your mouth with a bunch of words.
They made him a reluctant leader of the movement.
Yeah.
Okay, because Einstein died a broken man in intellectual terms. He never could figure out the grand unified theory. So he was a little frustrated that he died 1955 before he could figure that out.
I think a lot of people are
But
saying.
he disagreed with a lot of stuff that everybody that came around him or after him, he disagreed with a lot of their stuff. But he couldn't do anything about him. They say, hey, you're our hero.
That guy's rolling around in his grave right now. Stop, please.
Okay, so here we talked a little bit the other day about this, which is Einstein's gravitational constant there. And we're not interested in all these little letters and variables and so on. We're just interested in one thing, and that's the cosmological constant. Okay, and that's that lambda g sub mu v. Okay. What's the issue? That, by the way, that's a tensor, and a tensor is simply a different version of a scalar, which is a vector is a complex scalar, a matrix is a complex vector, and a tensor is just a complex matrix. It's just a more sophisticated matrix. People understand more or less what a matrix is. Tensor is the same thing. That's why you have the 1, 2, 3, 2, 1, 7, 5, 4, because that's what the mu v represents. But we're not interested in all this stuff. We want to understand what this means.
We're just talking about a position on a graph?
No.
Is that what these are?
Yeah, no, it's just, see, because this is an equation that represents many equations, okay? So you got to look at it like that. But what we're interested in here is what does this mean in physical terms? And the one I want you to focus on is the cosmological constant, which Einstein had quite a bit of trouble in. He put it in, he took it out, he put it in, he took it out. He didn't know what to do with the
playing with it,
cosmological constant. And the important thing there is, first of all, that is the variable in this equation that represents dark energy today. And I want to focus on the word constant. I want you to see that it is a constant, okay? I want you to keep that in mind throughout the chat today, okay? It's a constant.
The G is a constant.
Yeah, the lambda is a constant, okay? The whole thing, this cosmological constant is a constant, okay? Hopefully people know what constant
is. It's a collection of...
Well, no, constant means it doesn't vary. There's no variable.
But the tensor is...
it's treated as a constant. Okay?
And a tensor is a collection of...
It's a matrix. Again, the best way to visualize a matrix, people more or less understand the word matrix. Tensor is just a matrix, okay? Just a more sophisticated one. But this is the point. Here we have it, okay? This dark energy is supposed to be the stuff that's pushing everything outwards.
The red stuff.
Okay? Yeah, it's the expansion of space and time. Okay, important to include time in there. But then the question is, what's the black stuff it's pushing against? Okay, that's important. And of course they say, well, that black stuff that's around it against which it's pushing, we don't know what that is, or it's an irrational question or unscientific question because we have no way of proving it through an experiment. Blah blah blah. Okay, so that's the answer to that. Okay, so that's what we're talking about. We're talking about the expansion of space-time. That's what you're staring at there, okay?
I wish you could do that in court. That's an unscientific question. Objection.
Okay, what's the problem with that? Well, all the galaxies are receding. You know, they're all redshifted according to the establishment, and redshifted means that something is going farther and farther away from you. If it was approaching you, it would be blue shifted. It's like the Doppler effect, you know. The train approaches you, you think, and when it passes you, you know, and so the lower pitch, that means it's receding, and that's what they're saying happens with light. We have a little problem with that, And the problem is that the local group, the galaxy which are in our vicinity, there's like 54 now. There used to be like 20. Now they found like 54 of them. They're all blue shifted.
Uh-oh.
And they're coming towards us. And so the question is, hold it, you have this balloon, right? It's expanding. All galaxies should be receding. But the ones in the local group are coming towards us. They're blue shifted.
How do they explain that?
Well, yeah, it's easy to explain.
Don't tell me an unscientific question. Come on.
No, it is a scientific question. Okay. They have a scientific answer. The answer is that gravitational forces and electromagnetic forces are overcoming the expansion of caused by dark energy. So dark energy does its as much as it can to push everything apart, but gravity, fortunately, whatever that is, and electromagnetism, whatever that is, are bringing everything in the vicinity closer together because they're too close to us. And the question is here, are they that close? I mean, you talk about Andromeda galaxy, right? And Andromeda is 2.2 million light years away. That's close enough for gravity to be pulling and electromagnetism to be pulling and overcoming dark energy, which is doing its best to push everything apart. So you got to think about that. And so here, I just wanted to point out, here's good old Andromeda, okay? Okay, that's what it looks like, and it's that's a big picture of it, but really it looks like a little dot in the sky. And you say, well, that's so far away. How come that one's not being pushed by all that dark energy that's pushing everything farther away? And remember, that galaxy that you're staring at there is bigger than the Milky Way, okay? So... And these are the two biggest galaxies in our vicinity.
What's the
Andromeda is the biggest one, and the second biggest one is the Milky Way.
What's the furthest blue shifted galaxy?
Well, the as far as I know, I don't know the answer to that, but as far as I know, only the ones in the local group are blue shifted. But I don't know if they found. I guess they found no other one because all the other ones are red shifted or far away. And the question is whether their assessment is correct.
Yeah.
And let me give you a different version of that so that for you to consider, okay? It's based on the rope model. If you take a rope, okay, any rope, and you string it across from one tree in the forest to another one far away, 2 kilometers away, okay? And you make it as tight as possible. You just whatever means you have for making it tight, you will note that closer to the ends, the links are shorter. And as you get to the center of the rope, to that whole space there, if you get to the center, the links are a little longer, okay? And that's all I want to show you. It's known as tired light. Okay, the phenomenon is known as tired light.
It'd be hard to see it with a good rope, though.
And there you have it. Okay, so you have two galaxies. Closer to the galaxies, you have high frequency, and the links are shorter. But as you get to the center between them, you would expect and here's exaggerated, but the point here is the links should get longer and longer. That means that if we're receiving signals from that center, they would be red-shifted. That doesn't mean that the galaxy is receding. It just means that we're staring at part of the rope that is red-shifted.
Yeah, so you're saying it's just far away doesn't mean going away.
Correct. It just means that the rope towards the center is going to look like red-shifted. And in the case of galaxies which are in our vicinity, well, they're blue shifted because they are coming towards us because of gravity. So I don't doubt that the ones close by are coming towards us and are blue shifted. It doesn't imply that the ones farther away are red shifted, meaning they are red shifted, but it doesn't mean that red shift means that they're running away from us.
Well, technically, blue shift also wouldn't mean that they're coming towards us. It could just mean that the light that they're giving off is intense enough in frequency that it just doesn't get tired by the time it gets to us.
My point is that there are other versions. Mm-hmm. That doesn't mean that the universe is expanding. And then you have the question of what do you mean the universe?
Oh yeah.
There's no such thing as the universe. A universe is a concept because it involves a relation between space and matter. That's what universe means. Space and matter.
Yeah.
So there's two thingies there and it can't be a thing then.
Which one's getting
And aside from the fact that you cannot make a picture of the universe because the universe is space and space is not a thing, therefore
can't take a picture.
It can't take a picture of that. It's nothing. It's that which doesn't have shape. That's what space is. So you can take a picture of all the matter if you had God's camera. You'd stay
all
far
the matter
away.
going away from each other. Makes more sense.
But you cannot take a picture of space. Sorry. And so space cannot be expanding, but it's not a thing. Okay. But then what happens? According to the establishment, we have this issue where you have gravity warping time, space-time, right? And what you're doing, not only warping space, you're warping time, because time is part of space-time. Is this structure, 4D structure, unimaginable 4D structure that they use in mathematics to try to not explain, but describe mathematically how gravity works. And so they say you have a mass, in this case the sun, weighing down this 4D canvas, which is made of space and time, three dimensions, as they call it, which are not dimensions, and time dimension. None of them are dimensions. They're all number lines, okay, because they're talking about math and about physics. But they warp them, and they say this is what causes the warpage of space-time. And because space-time is warped, then the Earth rolls around like the little ball on a roulette. Okay, that's why it can't fly away from from the sun, from the solar system. But then the question, if that's space and time, what is the black stuff that gives contrast to the net? And of course, they never answer that question. They say, well, it's an irrational question.
There's a lot more
because
problems with it.
You're not supposed to take it literally, the analogy.
There's a lot of problems with that. Why aren't people being crushed? Why can people go to the moon? There's a lot of
But I think the main one here is that, that you're warping time. That's what I want you to focus on, because we're talking about dark energy. And so we have two issues here. The first one is that gravity is the warpage of time. Let's forget about space for a second. We're going to warp time, right?
Okay.
That's what we're doing with gravity. But then we have dark energy, and that's pushing everything apart, okay?
Yeah.
And what did we say at the beginning? We said we have this explosion, and this time is, expanding out there, and that's what's pushing, the galaxies and the stars and the planets apart.
Okay.
So we have two things. We have a planet, a mass, right, weighing down space-time, and then we have space-time, time really, let's forget about space, time also pushing, expanding, because you had that balloon, right, it was pushing everything apart. That's time expanding there. So time doesn't only warp, time also expands. It's getting it's bloating.
Yeah.
Okay? And so
I never thought about that. Yeah.
Here we have one aspect of that. That's the time bending. That's one aspect that they want to give you. Okay, but then it's doing this as well. It's also expanding while it bends.
Lego says they can't draw it. You just put the word time.
Yeah. It's bending time, but at the same time that time bends, it's also expanding. So time. Time is doing two things, so keep that in mind. It's very dangerous. I mean,
that's stupid. You have to just write the word time because they don't have a picture.
Okay, so I hope you understand what's happening here. Not only is time being used to explain gravity, which is really the opposite of what they're talking about, because they say dark matter causes gravity. Why? Because it weighs down space-time. So now you're bending time locally. But then you have this time thingy which is expanding, pushing everything apart, which is against gravity. So the anti-gravity is dark energy. It's made of time, right? But at the same time, it's also part of gravity, which is what is bending to explain gravity locally or in our neighborhood.
I need more shots.
But now let's throw in there a couple more problems with that. The first one is that, what did I say at the beginning? That cosmological constant was dark energy. It's a constant.
Yeah.
But time is not constant. So there's a contradiction, because dark energy is this expanding time, which is variable, and they're talking about because it's expanding and bending and doing all this good stuff, but the gravitational constant that they're using is a constant, meaning it doesn't vary.
But if the
I'm going to add another one now.
But is it a number that's constant or a relation that's constant?
It's a variable.
The lambda g.
It's a component of Einstein's equation that is a constant.
But
okay?
Is it a relationship that's constant or is it actual variables that's constant?
What do you mean a relationship?
Like, for example, E equals mc squared, that could be constant even though the variables are changing.
Yeah, if they all increase at the same time.
That's what I mean.
But here you have that whole unit,
like
which is supposed to be a constant because it's called a constant, but at the same time, it represents the dark energy, which is what these people are investigating mathematically and also the astronomers. But here you have a contradiction because in one instance they treat it as a constant, in another instance they say, well, this dark energy is pushing everything away, but that dark energy is what? Dark time, really, right? And so you have this expanding, this variable compared to a constant. But let me add one more in there, just to throw it in there.
I wasn't confused enough.
No, now you're going to be confused forever. Yeah. You have Heisenberg's uncertainty principle, or principle of indeterminacy, whichever way you want to call it. Okay, so you have this Heisenberg's uncertainty principle, which applies to quantum mechanics, which is the world of the small, right? But Heisenberg's uncertainty principle has two versions. One is that if you have the more you know about position, the less you know about motion, okay, about displacement. And the more you know about displacement, the less you know about position, which I like to say is, the more the ball stands still, the less it moves, and the more it moves, the less it stands still.
No shit.
Okay, that's one aspect. But then there's another aspect. This is where you got to hold on to your bridges. Okay. The more you know about energy, the less you know about time, and the more you can measure time, the less you know about energy. And here we have dark energy being pushed everything aside, which is made of time. But here they're saying that the dark time is the same thing as the dark energy, because energy is made of time. In this gravitation, in this constant, in the constant. So you have two issues here. You have the world of quantum mechanics that says the more you can measure the energy, the less you can measure time, and vice versa. And here you have energy, which is made of time.
Done. You're done right there already.
And we have a contradiction there between quantum mechanics and
time.
But then how do they plan to reconcile general relativity, which says this nonsense, to quantum mechanics, which is another nonsense?
Isn't that why they're never going to get to the gut?
I mean,
you said earlier that Einstein.
People are talking about it anymore.
You were saying that Einstein must have. He died intellectually bankrupt because he couldn't figure out the gut. But I think a lot of people are in that predicament right now. Like actual physicist quotations. Let's just say people who are interested in the subject who can't figure it out.
Yeah.
There's a lot of them.
But this is the problem. The problem is that you have all these astronomers, all these theoretical physicists, and they're working on these things.
And they're looking for nothing.
They're looking for dark energy and dark time. So
I need you to look for something that's invisible. Gotcha, boss. It's like Three Stooges or some shit.
More or less. So here's the conclusions for today, okay? We have conclusions. We have relativity. The universe is expanding. That's what relativity says, right? So here are some of the questions for you to ponder or ask people that are knowledgeable.
That's something I was going to ask you. Is there more dark energy being created every second?
Yeah, of course.
Even though it's a constant.
Yeah, and that's why time is expanding, because we're creating more energy, more time as time goes by.
And so we're creating more time as time goes by. We're done.
It says, is matter exploding or dispersing, right? Is it matter that is separating like a hand grenade? Or is it space that is expanding, or both? And they say it's both, okay? So we have both.
So nothingness is getting bigger.
Yeah, then the other issue is redshift proof that galaxies are receding, is blue shift proof that the nearby galaxies are overcoming dark energy and coming together. Is what's happening here? Is the redshift proof that everything is exploding? Is blue shift proof that everything's coming together? And so these things have to be addressed, because right now all the theories are based on this red shift, blue shift thing. Then you have relativity. Gravity, what is it? Warp time. That's what gravity is under relativity.
Yeah.
Warp time. And then, but gravity is also, gravity pushes inwards because that's what gravity is, whether it's pushed or pulled. But they always have a push because when you have that depression, why does it fall downwards into the hole? But the question is it pulling or pushing? So
it doesn't matter.
yeah. So they always have push gravity. And dark energy does the opposite, pushes outwards. So one pushes inwards, the other one pushes outwards. They're against each other, right?
As an aside, I would love to see you interview a physicist. Just you interview them.
Okay, so here we have dark energy. What is that? It's the expansion of space-time, right? So let's forget about space for a second here. It's the expansion of time. Yeah. But the cosmological constant is constant. It doesn't expand. It's supposed to be constant. And but we're saying that it is, dark energy is actually expanding.
Dark energy has time in it. It's getting bigger.
So it can't be a constant on one hand and also be treated as something that expands or changes, right? Then you have Heisenberg's uncertainty principle, right? You can't simultaneously measure energy and time, right? You can't do both of them at the same time. So we have a problem because energy, dark energy, is time. And so I'm suggesting, that maybe what we should do is call it dark time from now. We live in dark times.
Yeah, we do. We live in dark times.
So we're living in very dark times, okay? And I haven't got to the extinction segment, but we'll do that next week.